Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, airplanes. Airplanes are the ultimate aerodynamic machines. They work with the air in many interesting ways to get something interesting done, to take you from one place to another through the air. To start with, airplanes are streamlined objects, which means that the airflow around them is essentially laminar the whole way. That's as opposed to what are known as blunt objects, such as a ball, that lose the streamlined flow partway through its passage around an object. So blunt objects create turbulent wakes behind them and experience substantial pressure drag. Airplanes and other streamlined objects try to minimize the size of their turbulent wakes and therefore experience as little pressure drag as possible. And they do a pretty good job of that. So, first observation about airplanes, not a lot of pressure drag. They do experience viscous drag because the air does rub across the sides of the plane. But viscous drag you can live with. Pressure drag, not so much. All right. How do airplanes keep themselves aloft? How do they keep themselves, in a sense, from falling? After all, gravity is pulling downward on the plane by virtue of its weight and pouring downward momentum into it. Every time every second of downward pull is an impulse. The weight times a second, that's a passage of momentum. Where does it go? Well, why doesn't the plane accumulate it? Because the plane passes off that momentum to the air. And that process of passing off momentum to the air involves the airplane's wings. The wings are themselves streamlined objects. They're typically described or called airfoils, shapes that are designed to minimize, first off, the turbulent wake, and second off, to manipulate the airflow in order to get lift forces that do things that are interesting. Now, the shape of a wing the shape of the wing and its angle into the onrushing air result in different airflows over and under the wing. The airflow that goes over an airplane's wing when it's flying properly, that airflow initially arcs upward, but most of its trip over that top of that wing involves a bend downward toward the wing. So the airflow initially bends upward, arcs then over the top of the wing, and that arcing downward toward the top of the wing is an acceleration toward the wing and therefore has to be caused by something. Something must be pushing that flow of air toward the wing. There must be a pressure imbalance between the pressure near the wing surface and far from the wing surface. Well, far from the wing surface, way out and high above the airplane, the pressure is atmospheric. So the air pressure right near the top of the wing must be less than atmospheric, so that there's a push downward due to a pressure imbalance that bends the airflow toward the wing. And sure enough, the air pressure over the wing is substantially below atmospheric pressure for much of the trip across that top surface of the wing. So low pressure above the wing. Below the wing, the air bends pretty consistently away from the wing. The wing, you can think of it like a paddle, which is a little bit of a simplification. But the air hits the bottom of the wing, particularly when the wing's angled with what's called its leading edge, the edge that first encounters the air, high. When that leading edge is high, the air is pushed downward. It can't go through the wing. It has to bend away from it. So that downward bend in the airflow beneath the wing involves a pressure imbalance again between atmospheric pressure far away from the wing and higher than atmospheric pressure near the bottom surface of the wing. That pushes the air down. So you have low pressure above the wing, that is lower than atmospheric pressure above the wing, higher than atmospheric pressure below the wing. That means the wing is experiencing a pressure imbalance across its two surfaces, top and bottom. and that pressure imbalance pushes the wing substantially upward. Actually, it's upward and a little downwind. The upward portion of that push is a lift force, and in this case, it's a lift force upward. Remember, the name lift force is a little bit of a misnomer because lift forces can be in any direction that's perpendicular to the fluid flow. You can get downward lift forces. This one's upward, so upward lift force, but there's also a little bit of force that is downwind due to these pressures, and that is known as induced drag. It's a new kind of drag force. We've talked about viscous drag, which is the rubbing effect of a viscous fluid on a surface. We've talked about pressure drag, which is the drag that shows up when you have turbulence and unbalanced pressures on an object. Induced drag shows up when you try to obtain lift, or when you are obtaining lift forces out of the passing fluid. The act of pushing the fluid to the side gives that fluid energy, does work on it, and gives that fluid energy. And where does the energy come from? It comes from the motion of the object obtaining the lift, in this case the plane and its wing. So the wing loses some of its forward momentum and kinetic energy basically given to the air. The air carries it away, alas. All right, so that's how a plane manages to get the lift force that keeps it in the air. This imbalance in pressure between the bottom and top surfaces of the wing, and the air leaves, as a result of this arrangement, the air leaves the wing not heading horizontally anymore. It is heading downward to some extent. It's been deflected. And that downward deflection of the air, so that the air is carrying downward momentum with it, it's carrying away the momentum that the plane was being given by gravity. So the plane doesn't accumulate downward momentum, stays up there. The air goes down in its place. There are sort of two schools of thought about the way in which airplanes fly. They're actually the same story, just viewed a little differently. The Bernoullian view is this pressure imbalance between high pressure below the wing, low pressure above the wing, leading to forces due to pressure pushing the wing up and a little backward. That's the Bernoullian point of view. The Newtonian point of view is just the fact that if you push the air downward so that it leaves the plane heading downward, it must have pushed you upward. Action, reaction, Newton's third law. Sure enough, the plane is pushed upward in the act of deflecting the air downward. But these two ways of looking at how airplanes fly are equivalent finally when you look into the details. It's not a big deal. All right, so that's the origin of lift in an airplane. How about the limits to lift? Well, the amount of lift that an airplane can get depend on the extent to which they deflect the air downward and how much air they deflect downward. So if an airplane has a bigger wing and hits more air, it can get more lift. Or if it's going faster and encounters more air with the wing that it has, it can get more lift. And if the plane tilts its leading edge, again, the leading edge is the part of the wing that first encounters the air, as opposed to the trailing edge, which last encounters the air. If the plane tips its leading edge high, so that the airflow over the wing is arcing particularly aggressively toward the top surface, and the air under the wing is arcing particularly aggressively away from the surface, that leading edge high arrangement, called angle of attack, creates more lift. You encounter more air, and you bend it harder. So those are things you can do to change the lift on an airplane. And for an airplane that is just trying to maintain constant altitude, it wants to make sure that it gets just enough lift to cancel its weight. So there's no net force on it, and it can be at constant altitude or constant rising or constant descending, but constant, not a big acceleration up or down. Some observations to make then about this is that planes that move faster can use smaller wings and less tilt, less angle of attack, because they encounter so much air every second. Whereas planes that travel more slowly, two-seater planes driven by a propeller that just can't go very fast, they typically need bigger wings and more heavily curved intrinsically, wings that really make the most of what little air they encounter every second. So the shape of the wing varies with the speed of the plane. And planes that are commercial jets, for example, that take off and land at relatively low speed in order to be safe and realistic, and yet fly at very high speed, and so on, they can change the shape of their wings so that when they take off, they extend their wings, enhance the curvature of their wings so that they can't encounter more air by virtue of traveling fast, but they can work with it harder. So they enlarge their wings at takeoff and landing, and then they shrink their wings when they're flying at high speed. So that's a familiar effect to people who've flown in planes and look out the windows and watched during takeoff and landing. The wings are bigger, they expand them. The limits to lift, let me go to that one, that if you keep on increasing the angle of attack of the wings, which you do by tilting the entire plane on virtually every plane. Now, most planes can't tilt their wings without tilting the plane. They're attached. So if you keep increasing the angle of attack by tilting the plane more, you bend the air more aggressively, which is seemingly good. It gives you more lift, and particularly if you're traveling slowly, you can get more upward lift despite not traveling very fast. But if you tilt the wings too far, they stop being streamlined and they become essentially blunt objects. They go from being slicing through the air beautifully to basically just hitting the air like a box. And that's not so good. The transition from one to the other involves the appearance of a turbulent air pocket behind the wings. So they're the transition from laminar to turbulent. And when the airflow behind the wing becomes turbulent all of a sudden, this is a phenomenon known as stalling. The wing stalls. It loses a lot of its lift, and it suddenly develops severe pressure drag. And this is not something anyone wants to experience in a plane, unless this is a teaching moment at high altitude and safety with an instructor. You don't want to stall the wings of a plane. What happens when you stall the wings of a plane is you tip the angle of attack too severely for the current situations, and the airflow over the wing fails to make it smoothly all the way to the back of the wing. It's the same phenomenon that occurs on the sides and back of a baseball, where the air going over the girth of the ball at low pressure tries to flow into rising pressure behind the ball and fails. In an airplane, same thing. You get very low pressure over the leading edge area of the top of the wing, and then the airflow tries to go into the rising pressure behind the wing, and it fails and creates an air pocket back there. That's the stalling effect, where the airflow on the top of the wing peels away from the wing and leaves a turbulent air pocket. So stalling is to be avoided at all, essentially all costs, and that limits how steeply the plane can tip itself and how rapidly it can rise, for example, as it takes off or I suppose is landing. It's a little more complicated landing, but in any case, no stalling. All right, how about how an airplane then turns? The way it turns is not like an automobile, where it's simply, if it's flying toward you, it just begins to deflect the air to one side or the other and uses that to create a torque that just changes the orientation of the plane like that. That doesn't work very well. It leads to planes flying through the air sideways, which is definitely not a thing to do. Okay, what they do instead is they tilt the entire plane they rotate the entire plane so the wings tilt. And that tilt of the wings means that the lift force, instead of being strictly upward as it is if, okay, I'll be the plane. When the plane is flying straight and true and everything's simple, the lift force is purely upward. But if they tilt the wings like this, now the lift force is this direction. It's up at an angle. So part of it is supporting the plane's weight, and part of it is causing acceleration to one side. And the plane will accelerate toward in the direction it's tilted, in the direction it's tipped. To keep that whole thing stable, they use the tail in order to make sure that they don't just accelerate sideways like this. They actually want to steer and face into the direction that they're heading. So that's done with the tail of the plane, again by deflecting the air. And I should point out that the wings are not the only, essentially, wings on the plane. The main wings support the plane. The rear elevators, which are in the tail, there are two more wings that are horizontal. And those allow the plane to tip nose low or nose high. They deflect the airstream as wings, not just paddles, but wings. They fly. They have all the airflow characteristics of the main wings. And they allow the plane to orient its nose high, nose low. And finally, there's the vertical fin that allows the plane to experience torques that aim its nose to the right or to the left. All right. In turning, they actually use the lift of the main wings to accelerate through the turn. What other things? During takeoff and landing and even in normal flight, to control how much lift they get, they often need to tilt the wings differently. If they tilt the wings leading edge high, that is a high angle attack, they'll get more lift. So during takeoff, when you want to go higher, accelerate upward, and you want more lift, you often will lift the nose of the airplane. Not because that itself causes the plane to rise, but because it increases the angle of attack of the wings. So they get more lift, and the plane rises. And during landing, they often reduce the angle of attack of the plane. It doesn't mean that they tip the angle of attack of the wings. They don't necessarily tip the nose low so you sort of dive toward the ground. All they're interested in is reducing the lift so that the plane is under-supported and it accelerates downward. And that can be done by slowing the plane down so you encounter less air, or by reducing the angle of attack of the wings so that they develop less lift with the air they do encounter. All right, so that's turning, steering, rising, descending. How about propulsion? Well, why do you even need propulsion? If the plane is cruising along at 30,000 feet at a steady pace, straight line, can it just coast all the way to its destination? After all, zero net force is what it's experiencing. And alas, no, it can't do that because it's experiencing all three drag forces. It's experiencing some viscous drag as the air slides past the skin of the airplane. It's experiencing a modest pressure drag. It's not perfect at controlling the airflow, so there is zero turbulence. There's some, and so it experiences some pressure drag. And lastly, because it's obtaining lift to keep itself aloft, it's experiencing some amount of induced drag. It's giving the air some of its energy. So it has to be pushed forward by something to compensate for the backward pushes that we can collectively call air resistance. How does it propel itself forward? It grabs the air and throws it backwards. It's basically swimming through the air. Grabs some air, throw it backwards. Grabs some air, throw it backwards. And there are two classic ways of doing that, of throwing the air backward. One is propellers, and the other is jet engines. And we can look at both. Propellers are basically rotating wings. This was a great observation of the Wrights. Orville and Wilbur Wright were not just hack bicycle mechanics who played around with airplanes. They were serious aerodynamicists, and they knew what they were doing, and they realized, really for the first time, that propellers, properly designed, are rotating wings. They are not paddles. that are just sweeping through the air and like ramps, pushing the air backward. That earlier concept of how a propeller behaves, what's the right kind of propeller, or even what's the right kind of fan, leads to stalled wings, wings that have turbulent air pockets behind them. So badly designed propellers produce turbulence and experience pressure drag and are very inefficient. So it was the Wrights who came up with the most efficient propellers for their era because they knew they were wings and designed them properly. So what do I mean by a propeller being a wing? That when it sweeps around in a circle, round and round it goes, the airflow around the surfaces of that sweeping wing flow, the air flows over both sides of it, of the wing, which in this case is the front surface of the propeller and the back surface of the propeller. Front being toward the front of the plane, out into the distance, and back being toward the back of the plane and behind it. So as the air flows around those two surfaces, it does everything the air does around the wings of the airplane. It experiences bends. First of all, it remains laminar to the extent possible. Skip the turbulence. The airflow around the front of the propeller should bend toward the propeller, meaning there's low pressure near the front surface of the propeller. So low pressure in front. The airflow behind the propeller, toward the rear of the plane, that airflow bends away from the propeller toward the rear of the plane, so there's high pressure behind that back surface of the propeller. So you got a pressure imbalance again across the wing. And the pressure imbalance this time, from high pressure behind, low pressure in front, pushes the propeller wing forward. That's the force that propels the airplane, is that difference in pressures between the front and back of the propeller. Necessarily, the propeller also deflects the air it encounters backward, toward the back of the plane, behind the plane. And if you throw the air backward, the air throws you forward, and so it propels the plane forward. So, propeller-driven planes spin their wings around in a circle, deflect the air backwards as a result, develop the right pressure imbalance to push them forward, and off they go. They do leave the air with some amount of rotary motion to it and angular momentum. And so that's actually a problem. You're giving away angular momentum to the air, it's going to give you the opposite angular momentum. So propellers do tend to twist the entire plane. And a solution to this is to put the propeller in front of the plane where the air that it throws backwards travels across the rest of the plane's surfaces and gives back the angular momentum that it would otherwise carry off into the distance. And so the plane now isn't struggling against this constant twist that comes from the propeller being twisted back by the air. Another solution is to have two propellers spinning in opposite directions, and this is also very common in airplanes. They don't spin them all in the same direction, give the air all the same angular momentum. They put in angular momentum one way with the left propeller and put it in the other way with the right propeller, and as a result they end up with no angular momentum in the plane. All right, so that's propellers. How about jet engines? And why jet engines first? Propellers can only propel planes so fast. It becomes very difficult to propel a plane faster than a couple of 100 miles an hour using a propeller. Why? It's the same problem as swimming super fast. If you're swimming slowly, you can grab the water, and throw it backwards. Grab the water, throw it backwards. But suppose you're trying to swim at 100 miles an hour. Then just to keep up with the passing water, you have to move your hands backward at 100 miles an hour every time you grab a chunk. And to get any propulsion, you have to go even faster. You have to grab the chunk of water and throw it backwards at 120 miles an hour. Otherwise, you're just keeping up with the water, or worse. The airplane has the same problem. In order to get any propulsion out of forward propulsion, what's called thrust force, forward, out of the passing air, when the plane's going very fast, it really has to be able to grab the air and throw it back really fast. And eventually this becomes impossible. They have to have the plane's propeller has to spin so fast that its tips begin to travel as fast as sound travels, or faster, the speed of sound. And that's a problem once you start having an aerodynamic object, an airfoil, move through the air at near the speed of sound. The idea that air is just an ordinary fluid, incompressible like water, life is simple, not so true anymore. Suddenly the air becomes quite compressible. And the rules that I've been following and the details I've been ignoring, you can't ignore them anymore. So you can't spin a propeller fast enough to work in air that's coming by at 400, 500, 600 miles an hour. That's too fast. You can't spin the propeller that fast. All kinds of problems show up when the tips of the propeller become supersonic. Set it aside. Don't use propellers to propel a plane at 500 or 600 miles an hour. Use a jet engine. And what a jet engine does is it takes the onrushing air, same air that the propeller would try to work in as the air is going by. Take that air and slow it down. How do you slow down that passing air? Send it into a diffuser. So an anti-nozzle. The air comes in, you spread it out, it will slow down and its pressure will rise. This is Bernoulli again. And that's what happens to the front end of a jet engine. The jet engine then works with the air with more little wings. It uses a compressor basically, which is more spinning wings. It packs the air more tightly, and now air really is a compressible fluid in this context for sure. It packs that air tightly. It does work on it too. Packs the air very tightly. The pressure rises. The speed is slow. So the air traveling through the jet engine is not traveling at 600 miles an hour like the air outside. It's been slowed down to 100 or 200 miles an hour, something in that territory. They put that air into a combustion chamber, put in fuel, and burn it. And suddenly the pressure doesn't change, but the volume of air expands enormously because the pressure can't change because the air enters the combustion chamber and leaves all in one environment. If the pressures were wildly different, it would accelerate toward the low pressure. So in the combustion chamber, the pressure is pretty much all the same. It's high because you pack the air in there, but it's relatively constant. But you sort of create more air, and you do this because for keeping it at the same pressure, but dramatically raising its temperature means that the density of the air has to drop dramatically. For the very hot burned gas, really, to maintain the same pressure, you got to spread out the particles. You don't need as many in the same volume. They'll make too much pressure. So they spread out dramatically. And it's as though you've suddenly created air out of nothing. Tons of air, lots of air. And that air goes roaring out the back of the jet engine through a nozzle, turns its pressure potential energy, you have large pressure, turns that into kinetic energy. And this vast volume of burned gas goes roaring out of the nozzle at phenomenal speed, much faster than any of those speeds up to now in the story, way more than 600 miles an hour, roaring out the back of that engine. And as though it were created out of nothing. It's not rocket propulsion, but there's a character similar to rocket propulsion. You've made this huge volume of gas and thrown it out very, very fast. It did happen to involve gas coming in, but that's not so crucial. And therefore, jet engines manage to throw a lot of gas backwards very fast, and the gas pushes back, action-reaction, and that propels the plane forward. As for jet engines themselves, there are two types in general. The first is just what I've described, what's called a turbojet. It compresses the air, burns fuel in it, throws the whole mess out in a nozzle, and propels itself forward by doing that. That turbojet concept is great. It's got a little bit of an inefficiency to it, and that comes about because it deals with only the air that it's willing to burn fuel in. That's all it can work with. It's a limited amount of air, but it throws that air back very fast. And so it conveys a lot of backward momentum to that air, in part by giving that air an extremely fast backward velocity. And very, very fast moving air carries with it a lot of kinetic energy. So they're getting the forward momentum they want, the jet engine people, the airplane people. They're getting the forward momentum they want, but at a cost of a lot of energy. It would be nice, instead of throwing, say, 1 unit of mass backwards at 10 units of velocity, and therefore 100 units of kinetic energy, because remember, kinetic energy goes as the square of velocity, or speed. Instead of using 1 unit of air and sending it super fast and letting it carry away too much kinetic energy, use more air and throw it away less fast. You can get the same momentum out of it, forward momentum out of it, but giving it less energy. In effect, grab more air and throw it back slow instead of grabbing a little air and throwing it back fast. This is the same concept you use in swimming, for example. You don't grab a little water and throw it back as fast as you possibly can. You grab a lot of water and throw it back more slowly. You'll get the same forward momentum out of it, but you won't give it so much energy. So how do they do that in jet engines? They use what's called a turbofan engine. And a turbofan engine is basically a turbojet engine with a fan around it. And the fan's job is to grab more air that they're not intending to burn fuel in, just air, and throw it backwards to join the flow that comes out of the turbojet engine. And use the turbojet engine's extra energy to do this, to throw the extra air backwards. So a turbofan engine uses a turbojet engine as a power source more than anything else. Not so much as a source of forward thrust, but as a source of intense engine power to run a fan. And the fan is a lot like a propeller. It's a rotating wing again, pushing the air backwards by the flows around the front edge, back edge, the whole works. The difference is the turbofan's fan doesn't operate in the open airstream at full speed, at the speed of the plane, 600 miles an hour. No, it slows the air down first in a diffuser. So the air comes into the diffuser, slows down to reasonable speeds, a couple hundred miles an hour, where the fan can work. The fan then pushes that air backward, and then they go out a nozzle again and speed back up. So the main difference between a turbofan and a propeller is the speed of the air in which they work. The propeller is unprotected, working in the passing airstream at full speed. The turbofan's fan is working in the duct, where the air is traveling slower. It's been slowed down, it will be speeded up, and the fan works on it in the middle. There is a variation on this whole turbofan concept, where instead of working with that duct, and the fan in the duct, take the duct off and let the fan work in the open airstream. And that's called a turboprop. It's a turbo propeller. It's using a turbojet engine as the power source for a propeller. And those are also common. A reason why you would do that, why would you ever? You're mixing stuff. The turbojet engine, because it compresses the air before it burns fuel in it, can operate in thinner air, less dense air, like high altitude air. So a turboprop engine, that engine, the real power source is a turbojet. It can operate at 30,000 feet because it compresses the air, works in compressed air. Whereas a normal engine, the engine like in an automobile, and the engine that's typically used to run a simple propeller plane, a two-seater, those internal combustion engines don't work well at high altitude. They can't deal with the very low density air that's present at 30,000 feet. So a turboprop, it's just a better power source for a propeller-driven plane. All right, so that's the whole story of airplanes, how they support themselves in the air using wings and the airflow around the wings, and how they control the amount of lift they get, their turning and steering and rising and descending, and how they propel themselves forward in view of the fact that they're encountering backward air resistance forces. They need to push themselves forward, and they do that by pushing the air backward. And with that, I will stop the story of airplanes.